Section: Introduction. In this section, we introduce our work on reflection in language models, which enhances their ability to adapt responses based on previous reasoning, ultimately improving output accuracy. We note that recent studies suggest that reflection arises from a model's interaction with reinforcement learning environments. To validate these claims, we propose a comprehensive framework for measuring reflection and consistently observe this phenomenon during pre-training. We highlight that a language model's reflective ability is crucial for tasks requiring complex reasoning. The success of test time scaling heavily depends on refining this reflective capability. While reflection has been reported to emerge only during post-training reinforcement learning, we challenge this notion by providing evidence that reflection occurs much earlier, even during pre-training, and can be found in less advanced models. Understanding how large language models develop capabilities remains an open question. Our analysis of reflective reasoning sheds light on the origins of this important skill. We face challenges in benchmarking reflection using existing reasoning datasets, as reflection is often infrequent and models show unique error patterns. To tackle this, we differentiate between situational reflection, where a model evaluates reasoning from another source, and self-reflection, where it assesses its own reasoning. We measure a model's task-solving ability when presented with misleading reasoning that leads to incorrect answers, allowing us to assess reflection throughout pre-training. For example, we illustrate a partially pre-trained model attempting to solve a coding task. Initially, it incorrectly repeats an output, but, after being prompted with its flawed reasoning, it successfully self-reflects and corrects itself. By introducing erroneous reasoning chains with elements like arithmetic errors and logical inconsistencies, we can control the level of reflection needed for task completion while maintaining the established reasoning format. Our approach enables the rapid and cost-effective creation of datasets, facilitating a thorough examination of models' reflective abilities across various domains. We develop 6 datasets covering mathematics, coding, logical reasoning, and knowledge acquisition to evaluate both situational and self-reflection. Our results show that reflection is widespread across domains, with simple prompts like "wait" helping models identify errors. Specifically, we find that 231 out of 240 dataset checkpoint pairs exhibit situational reflection, and 154 pairs show self-reflection. As pre-training increases, models correct more errors, demonstrating a strong correlation between accuracy and pre-training compute. In summary, our contributions are threefold. We present a systematic method for creating datasets to study reflection. We show that pre-trained models can use simple prompts to correct prior reasoning across various domains, and we observe that improved pre-training enhances reflection, requiring fewer tokens to solve tasks. Section Summary. In this section, we propose a comprehensive framework to measure reflection in language models, demonstrating that reflective reasoning can emerge during pre-training rather than exclusively in post-training reinforcement learning. Our analysis reveals that even less advanced models can exhibit reflection capabilities, which improve with increased pre-training, allowing them to correct errors in reasoning across various domains. Section: Adversarial attacks on LLMs. In this section, we discuss adversarial attacks on large language models, LLMs. Adversarial inputs have been used for a long time to reveal weaknesses in neural networks. Recently, similar methods have shown that LLMs can be vulnerable to carefully designed prompts. These attacks have successfully targeted aspects like policy alignment, safety, and robustness, exposing significant weaknesses. While some approaches suggest adversarial training to strengthen models against these attacks, our main focus is not on showcasing these vulnerabilities. Instead, we aim to demonstrate how such datasets can be effectively used to evaluate reasoning abilities. We also address the trade-off between training time and testing time. As advanced reasoning models increasingly rely on computational resources during testing, discussions about optimal resource allocation have resurfaced. Previous research has explored the balance between training and testing compute, as well as the effects of techniques like supervised fine-tuning and reinforcement learning on reasoning performance. Our contribution is to show that certain reasoning skills can develop during pre-training, even without fine-tuning or specialized testing techniques. This suggests that we can instill important reasoning capabilities through pre-training alone, which may alter how we think about resource use in training and inference. Our goal is to measure reflection in a comprehensive and scalable way. We define reflection, create tasks to encourage it, and rigorously assess its presence. Reflection, as we define it, involves examining information, evaluating the reasoning behind it, and adjusting future actions based on that evaluation. We create two scenarios to elicit and measure reflection: situational reflection, where a model reflects on information from another source, and self-reflection, where a model considers its own outputs. We further categorize reflection into explicit and implicit forms. Explicit reflection occurs when a model acknowledges mistakes in its outputs, while implicit reflection happens when a model successfully navigates challenges without explicitly identifying errors. To elicit reflection, we introduce an algorithm that generates adversarial datasets designed to prompt reflective behavior from language models. This algorithm creates adversarial chains of thought, COTS, that lead to incorrect answers, mimicking human reasoning errors. In both scenarios, when we provide these COTS, models must reflect on the mistakes to find the correct solution. We believe these settings are essential for a thorough study of reflection. Our task design includes a trigger token to encourage ongoing reasoning. We propose an automated method to measure the reflective capabilities of models using these adversarial datasets. For explicit reflection, we develop a prompt-based classifier that detects when a model's output acknowledges errors in the adversarial context, regardless of whether the answer is correct. For implicit reflection, we consider any model output that leads to a correct answer in an adversarial context as reflective, even if it doesn't explicitly mention reflection. This aligns with our understanding of reflection in human cognition. Consequently, outputs that yield correct answers but are not flagged by the explicit classifier are classified as instances of implicit reflection. Further details on our reflection metrics can be found in the relevant section. Section Summary. In this section, we explore adversarial attacks on large language models, LLMs, to evaluate their reasoning capabilities through reflection, distinguishing between explicit and implicit reflection. We introduce an algorithm to generate adversarial datasets that elicit reflection behavior, allowing us to measure how well models can recognize and correct mistakes in their reasoning processes. Section: Experimental Setup. In this section, we outline our experimental setup to thoroughly investigate reflection. We assess partially pre-trained models with varying computational resources, focusing on differences in the number of parameters and training tokens. Our research includes two adversarial tasks: 1. Situational reflection, where we generate adversarial chains of thought from existing datasets using advanced models, and 2. Self-reflection, where we derive these chains from the model's own previous incorrect answers. We also check if the model outputs show clear reflective reasoning. We work with several model families. Olmo 2 is an open-source project with training checkpoints for models with 7 billion, 13 billion, and 32 billion parameters. We evaluated 40 checkpoints, aiming for evenly spaced options. For Qwen 2.5, we looked at its variance with 0.5 billion, 3 billion, 7 billion, 14 billion, 32 billion, and 72 billion parameters. Our evaluation of reflection spans a variety of tasks, creating 6 adversarial datasets based on Big Bench Hard, Crux Eval, GSM-8K, GSM-8K Platinum, and Trivia QA. We use models like DeepSeek v3, GPT-4o, and sentence transformers, along with automated checks and manual reviews, to ensure the quality of our datasets. For situational reflection datasets, we follow a multi-step process where we prompt a language model to create adversarial chains of thought. If the original tasks don't include these chains, we generate them using advanced models. We then introduce errors to create adversarial chains while ensuring they don't reveal their misleading nature. Our pipelines are designed to minimize errors and can be adapted to various domains. For self-reflection datasets, we run the language model on the base task and gather chains of thought for questions it answered incorrectly. We focus on questions that all checkpoints got wrong to maintain consistency across pre-training stages. More details about our dataset processes can be found in the appendix. Regarding metrics, we measure accuracy as the proportion of tasks the model solves correctly. We also use our explicit reflection classifier to assess the explicit reflection rate, which indicates how often the model shows explicit reflection, regardless of correctness. We report explicit reflection accuracy, which combines correct answers with explicit reflection, and implicit reflection accuracy, which counts correct answers without explicit reflection. We provide details on accuracy metrics in the appendix and report pre-training compute as the product of the number of parameters and training tokens. To classify explicit reflection, we developed a prompt-based classifier using DeepSeek v3, which is trained with examples of reflection. We validated this classifier against human annotated labels on several benchmarks. While it may miss some reflection instances, its precision is high, ensuring confidence in our reported findings. Our infrastructure utilizes the VLLM inference framework for hosting Olmo 2 and Qwen models, with DeepSeek v3 hosted on SG-Lang. We employ a cluster of AMD Michigan 300X accelerators and Kubernetes for job scheduling. Section Summary. In this section, we outline our experimental setup to study reflection in language models by evaluating partially pre-trained models across various computational budgets and adversarial tasks, including situational reflection and self-reflection. We detail our dataset creation process, metrics for evaluation, and the infrastructure used for hosting and running the models, ensuring a robust analysis of reflective reasoning capabilities. Section Results. In this section, we measure reflective reasoning across various domains by using our classifier to distinguish between explicit and implicit reflection in tasks like BBH, Cruxevil I, Cruxevil O, GSM 8K, GSM 8K Platinum, and Trivia QA. We were surprised to find a strong presence of reflection, which increases with more training resources. As pre-training continues, models show improved recovery from confounders, with explicit reflection becoming more frequent and contributing significantly to this recovery. We found that explicit situational reflection is evident in nearly all models. Except for the Cruxevil I task, every Olmo 2 pre-training checkpoint shows some recovery from situational confounders, either implicitly or explicitly. This leads to 231 out of 240 dataset checkpoint pairs showing at least one instance of situational reflection. To support our hypothesis that models develop explicit reflection over time, we expect most recoveries to be linked to explicit situational reflection. Essentially, we are looking for an increase in A. Recovery from situational confounders, B. Explicit reflection on these confounders, and C. Recovery through explicit reflection as we increase pre-training resources. The strong positive correlations we observe suggest that as pre-training increases, models are better at solving challenging instances and prefer explicit reflection. For example, in GSM 8K Platinum, we see that with more pre-training, models solve most tasks by explicitly reflecting on their errors. Trivia QA is an exception, where improvements are largely due to implicit reflection, as the task mainly assesses knowledge acquisition. We also explored the impact of the wait trigger on model performance in GSM 8K Platinum. We compared performance with no trigger and with the trigger that includes the phrase, "Wait, I made a mistake." Our findings confirm that even without a trigger, models improve their success on situational confounders as pre-training advances. The wait trigger clarifies its role. Models perform better when they can reflect explicitly. We found that the performance with the wait trigger can be expressed as a combination of explicit and implicit reflection rates. The trigger significantly boosts performance by encouraging explicit reflection, which increases with pre-training. Regarding explicit self-reflection, we initially viewed its rarity as a negative outcome. However, this is understandable since models are evaluated on difficult instances they answered incorrectly. Still, About 64.2% of attempts show some self-correction ability. We plotted the rate of reflection generated by the models, independent of task success, revealing a trend where models improve at explicitly identifying their errors as pre-training progresses. For Cruxevil I, we noticed that while models learn to self-correct with more pre-training, they can self-reflect much earlier. This suggests a natural development of self-reflection skills before self-correction. We believe there may be a critical threshold of pre-trained self-reflection that leads to effective reasoning during testing. We were surprised to observe such levels of explicit self-reflection from organic web datasets, and identifying data distributions that foster this reflection during pre-training is a logical next step for our research. Detailed results for all tasks are available in the appendix. Section Summary. In this section, we measure reflective reasoning across various tasks and find that models exhibit a strong presence of explicit reflection, which increases with more pre-training compute. We also observe that while models can reflect without prompts, the wait trigger significantly enhances their explicit reflection and accuracy, and although self-reflection is less common, it improves with pre-training, suggesting a potential pathway to developing autonomous reasoning abilities. Section. One can trade training for test time compute. In this section, we explore the balance between investing more in training time and the resulting costs at test time to achieve similar accuracy on downstream tasks. We estimate the training time cost as 6 times the number of parameters multiplied by the number of training tokens, while the test time cost is calculated as 2 times the number of parameters multiplied by the total number of words needed to answer a set of adversarial questions. We start by defining specific targets for the number of adversarial questions we want to answer correctly and plot curves for each target using the GSM-8K Platinum adversarial dataset. We employ a sequential test time scaling method by adding the trigger wait to our model's outputs, even using it twice to help weaker models match the performance of stronger ones. Our findings, illustrated in a figure, show that as we increase the training time investment, the requirement for test time decreases in the OLMO 2 to 32B checkpoints. This supports our idea that models improve their reasoning with more pre-training, leading to lower test time costs for the same accuracy level. To investigate if this trend holds for stronger model families, we present the results of Quen 2.5 on our adversarial tasks. Similar to our findings with OLMO 2, we observe that as we increase the pre-training compute, specifically the number of parameters, the model's performance on adversarial tasks improves consistently. This reinforces the notion that models can better tackle tasks even when they make errors in earlier reasoning, thanks to increased pre-training compute.